Today I want to talk about one of my favorite scientists, and this is a guy by the name of Robert Boyle, who was around in the 1600s. Robert Boyle is one of the founders of chemistry. He's known as the father of modern chemistry. There's a few of them. Antoine Lavoisier also has that designation, but Robert Boyle is one of the guys who brought chemistry from the Dark Ages, brought alchemy into a more legitimate science, which was chemistry. So he was really considered an alchemist in his day, and he was one of the first people who did experimental science and believed in the idea that science should be shared with the public and should be shared with the people, and that there should be a group of scientists that get together and talk about science with each other, so as not to kind of be secretive and hoard knowledge, but so that everyone can learn from each other and grow the discipline. So I'm a huge fan of Robert Boyle. He's kind of the master of side-eye, as you can see here in this photo. You always see him in these fetching long wigs, which were just very apropos of the day. So I am a huge fan of Robert Boyle. He was kind of an Irish-English chemist, and he had this interesting relationship with both England and Ireland, because he's British kind of by birth, but grew up in Ireland. And if you know anything about history, you know that England and Ireland have had a long history of not getting along very well. So he had this kind of interesting background. He wasn't the oldest child, but he came from a wealthy family, so he was in kind of a weird kind of lineage situation too, where he wasn't going to inherit land, so he went off and got an education, and that education was built around science. So huge fangirling about Robert Boyle. So let's talk a little bit about what he did. He did a lot of things for chemistry, but one of the most important things that he did, and one of the things he's best known for, is Boyle's Law, which is really all about gases and the study of volume and pressure of gases. So here's his dates here: 1627 to 1691, pretty early on in the history of science, in the history of chemistry in particular. And what he found in his study of gases is that the volume of a gas is inversely proportional to its pressure. And so before I kind of get into the logistics of that, I want to talk about the pressure of gases, or just the pressure in general. Pressure in general is the force per unit area. So if we think about this from kind of a conceptual standpoint, if I want to increase the pressure of something, then I can either increase the force that I'm applying, or I could decrease the area, one or the other. Both of these things would increase my pressure, right? Those are two ways that I can make my pressure go up. I think about this when I think about cats, because I'm kind of well on my way to being a crazy cat lady. And if we think about cats, if you've ever had one jump on you, right? You're like laying down on the couch, you have a cat jump on you. Think about a cat as like a mass. Let's say that I have a textbook that's the mass of a cat. So let's say I have an especially rotund cat, like a 20-pound cat. And if I had a 20-pound textbook and I had it laying on my chest, then I wouldn't really notice it all that much, right? And you can even kind of do this at home. Put a textbook on your chest as you're laying down. You don't really feel the pressure, right? If you're picturing kind of the force per area, it's spread out enough because the area of your textbook is reasonably large. But if you take that same mass, so that same weight of that cat that's on its tiny little paws, little bar stool paws, and you put those paws on your chest, then it feels like that cat is going to go through your chest, right? Have you ever experienced that, where an animal jumps on you, those tiny little paws put all that pressure, right? It feels like more than your 20-pound cat or whatever it is. So when I'm thinking about pressure, I'm thinking about cat paws. But it's really all about either increasing the force, so I'm putting more mass on there, and then the gravity is pulling on that mass in some way, or I'm decreasing the area around which I'm applying it. For gases, the pressure comes from those gas particles striking the sides of a container. So the pressure for a gas comes from these particles banging into the sides of a container. Gases are fast moving, small particles. They're kind of zipping around, and whatever container they're contained in, whether it's a classroom or an apartment or a flask or a scuba tank, then it's going to be pushing against those sides and applying some sort of force on the area that it's hitting. And so that's where the pressure of a gas comes from. When you talk about increasing the pressure, then you're doing things that are going to increase the collisions of those gas particles with the sides of the container. Now the SI unit for pressure is the Pascal, and it's abbreviated with a capital PA. There's a number of non-SI units for pressure. Pressure is one of those weird ones that's not very standardized. We see with units that it's usually like, it's either the SI system or it's the US customary system. And with pressure, I think because there's so many applications of pressure, there's actually quite a few different units that are used. So atmospheres, for example, are used here on Earth because we're talking about our atmosphere is 1 atmosphere. And if you have greater than 1 atmosphere of pressure, then you might be underwater, for example, you'd have greater than the atmosphere. If you have less than an atmosphere, that could be like when you're going up over the pass, on a mountain, then you'd have less atmosphere above you, less than 1 atmosphere. So it's really legitimately talking about the pressure coming from our atmosphere as it pushes down on us. There's also millimeters of mercury, which is kind of a weird one because millimeters of mercury is a length, right? And millimeters of mercury is a liquid metal. This refers to barometers. So barometers have kind of a pool of liquid mercury. This is not going to be the best picture in the world. That might shock you. So there's a pool of liquid mercury and a tube that comes up. And then the atmospheric pressure pushes down on the pool of mercury, and the mercury goes up the tube. And then there's, hash marks along the tube, and you can measure the length of the height of the mercury there. And that millimeters of mercury tells you how much pressure that it's pushing down. You push on one, it goes up the other, right? It's the way the barometric pressure works when you're looking at the way the weather systems change is related to the changing atmospheric pressure. Torr is another unit, and torr and millimeters of mercury are the same. And then bar is another one that is used in the imperial system back in the day. So you'll still see a lot of, even some of the National Observatory kind of data that are in bar or millibar. So that's a pretty common one. When we are using the SI unit for pressure, the Pascal, we tend to use kilopascals because of the magnitude of the unit itself, even though the SI unit is really the Pascal. In terms of relationships between them, 1 atmosphere is equal to 760 millimeters of mercury. Can you see that? Yeah, sort of. 760 millimeters of mercury, which is equal to 101.3 kilopascals. Just if you're going back and forth between those, then this is kind of a handy conversion factor. And of course, the volume of a gas is just the amount of space that it takes up. And for most of the gas laws, and we'll talk about exceptions to this in future videos when we talk about real gases, for most gases that act like ideal gases, the volume of the gas is going to be the volume of the container, because gases fill the space that they are in. And so we just can assume that the amount of space they have is the amount of space that they're taking up. So we're looking at how these two things are related to each other, how much space the gas is taking up, and then how the pressure, if I change the pressure, how that would impact the volume, or vice versa. If I change the volume, how would that impact the pressure? I like to think about it in terms of pistons. So you can see my very well drawn pistons here. If I have gas molecules, let's just make them little X's in here. So if I have my gas molecules in here, and I don't change how many I have, so I still have the same number, they wouldn't be that well organized, but for the purposes of fast drawing, they are. So I haven't changed the number of particles that I have in there, and I'm not changing the temperature. I'm just focusing on the volume, the space that they take up, and I'm going to apply some pressure to them. So in kind of situation 1 here, I have a specific volume, the amount of space that it takes up, my V1, let's call it. And then based on the position of my piston, I have some sort of pressure that's associated with my gas. Now, if I push down on this piston, I'm going to make the volume that it takes up smaller. So now I have a new volume. And what do you think that's going to do to my pressure? Well, it's not going to stay the same, right? There is a relationship between the two. And you can see even that it's more cramped looking. And that more cramped looking is going to cause more collisions with the sides of the walls. And the more collisions you have with the sides of the walls, the greater the pressure. So my P2 then is going to be a greater pressure than my P1. Okay, so that change in volume results in a change in pressure. But when I make the volume smaller, then my pressure goes up. So we say that these two variables, volume and pressure, are inversely proportional to each other. So let's look at kind of how that plays out mathematically. When things are inversely proportional, when I multiply them together, so I multiply my initial volume times my initial pressure, that's going to give me some constant C. And then if I change one of the variables, so I changed my volume in my piston example, that gives me a new pressure, right? So this one went down, but this one went up. It's going to give me that same C value. They're inversely proportional, and that proportionality means that they're going to be equal to a constant. And because they're inverse, when you multiply them together, it equals a constant. So therefore, you know, if they're both equal to the same thing, we can set them equal to each other. So V1 P1 is equal to V2 P2, which is an exceptionally fun law because it sounds like droids on Star Wars. So that's kind of exciting. I like the gas laws for that in particular. And this is Boyle's law, named after Robert Boyle, who's the one who studied them. Robert Boyle of the side-eye and the fancy wig. Now, if we use kind of that equation to solve a problem, if I have 2.2 liters of nitrogen, I have a given pressure, then when I have the volume, then what happens to my pressure? Well, it's a pretty straightforward algebra problem. We can kind of list out the variables we have. So my V1 is equal to my initial volume, 2.2 liters. My P1 is equal to 1.75 atmospheres. I've changed my volume, so I'm given a new volume, 1.1 liter, and it asks for what my new pressure is, so that's going to be my unknown that I'm solving for. So when I'm solving problems like this, if I'm just doing some algebraic rearrangement, I like to solve the variables first. So I'm solving for P2, so that's going to be equal to V1 P1 over V2, and then I can plug in my values. So if V1 is equal to 2.2 liters times my P1, 1.75 atmospheres, divided by my V2. Now, if I'm analyzing this, there's a couple important things that I'm looking for. So before I even plug it into my calculator, I want to have an idea of what my answer is going to be. So first I'm going to look at the units. When I divide out these liters, I'll be left with an answer in atmospheres, which is going to answer my question. It's asking for a new pressure in atmospheres. This equation, the way I've set it up, is going to spit out atmospheres. So that's good. Now, am I expecting a number that's bigger or smaller? Well, my volume is going down, so I'm expecting my pressure to go up. So I'm expecting that my pressure is going to be larger than 1.75. And when I look at my sig figs here, I have 2 in each of my volumes and 3 in my pressure. I'm multiplying and dividing, so I need to round my answer to the lowest number of sig figs. So I know that my answer is going to have 2 sig figs in it. That's what I'm going to have to round to. So when I plug that in, I end up with 3.5 atmospheres. And I wouldn't be surprised by that, right? It's larger than I was starting with by double, right? Which makes sense because I halved my volume and I have 2 sig figs in my response. So pretty straightforward in terms of algebra. Pretty cool guy in terms of a chemist. And if you have any questions on Boyle's law, don't hesitate to reach out.